Good afternoon, everybody, and welcome to the second of today's webinar sessions from Smart Vision Europe. We're looking at the theme of healthcare analytics, and we're looking in this session at regression techniques for healthcare. If you haven't joined in these sessions before, you should be aware that they are recorded, so you'll be able to listen to them again afterwards. There is some slideware here that I'm using, so if you like, we can email out the links to you to download the materials after the session is ended. And if you find it useful for our colleagues who are unable to attend today, then the best thing to do is just to reach out and send us an email, and we'll see if we can rerun it specifically for them. Now, with regard to asking questions, all the lines are muted, so we ask you to use the chat panel. If we run out of time, we'll follow up with you offline. If you don't know who we are, Smart Vision Europe are a technology company. We're a gold accredited partner to IBM, as well as a company called Predictive Solutions and Data Robot. We specialize in advanced analytics and data science, machine learning type technologies, and statistics support. We work heavily with SPSS and the SPSS product line, but we also work with open source technologies such as R and Python and Spark. We're a relatively small organization. We're made up of a team of people who have a long background in the analytics industry. Most of us have worked for SPSS Incorporated at some point in time, with 15 to 30 years experience working in statistics and data mining and machine learning and all that kind of stuff. Now that means that we've got quite a lot of experience of applying these types of applications, these types of analytical techniques across many different sectors, both within the commercial realm and the not-for-profit realm. And that includes, of course, healthcare. And we're going to be talking about today how you might apply regression techniques in healthcare. So we're going to start off talking about exploring relationships between scale variables with correlations that will help us introduce the topic of linear regression, simple linear regression. And we'll then look at a worked example of using multiple linear regression to model regional per capita cancer and mortality rates. We can also touch upon identifying problems in linear regression models before we switch it up to looking at logistic regression and working with logistic regression to model low birth weight. So regression is a generic term. People often say when they say regression, they kind of assume that they're talking about linear regression. In fact, it's a generic term. There are different types of regressions out there. It's a family of statistical techniques that they use to predict outcomes and generate estimates for thousands and thousands of applications. Linear regression is used when the outcome is continuous, or it's numerical an outcome. It's scaled data. And the relationships between the fields can be described using a straight line relationships. Logistic regression is used when the outcome is a category field or series of categories. Could be binary, could be two categories, or could be multiple categories, in which case you would use something called multinomial logistic regression. And then there are other flavors of regression which deal with purely linear relationships, such as quadratic regression. And finally, there is a type of regression, Poisson regression, which is used to model count data. That is data where you're trying to work out the probability of incidents occurring, independent incidents. So it's used in things like trying to model never events and trying to model things like insurance claims, that type of stuff, how many insurance claims a policy is likely to make. Usually, Poisson regression, you're talking about occurrences that occur typically less than 10 times across a given time frame. Okay. So examples of linear regression in healthcare, modeling the relationship, let's say, between blood pressure and diet is a possible application, or estimating costs. It could be a numerical outcome, like a monetary outcome, like costs based upon comorbidity, for example, or predicting some sort of physical attribute like visual acuity based upon the treatment that people have had or their age-related factors, or estimating some sort of mineral level or vitamin levels, such as calcium levels based on vitamin D levels, or age and sex, or mixing in demographic fields, or predicting something like recovery time or length of stay based upon demographics, severity of illness and treatment factors. So regression is actually shortened term, the larger term or the wider term, regression to the mean. That's a short form regression to the mean, which means falling back towards the average. And typically one would represent a regression, a simple scatter plot. Here we have the relationship between percent unemployed on the x-axis, the horizontal axis on the y-axis. Here we have percent reliant on public health care. This is US data, where each point in the scatter plot represents a particular region. In fact, it's a US county. And we can see that there is a roughly linear relationship here in the sense that the higher the percent of people who are unemployed in that particular county, the higher the percent of people who are reliant solely on public health care, not on private health care, because they're both obviously measures of, well, to a degree of economic hardship. So regression to the mean, where does the mean come from? Well, if we were to take the average of one of these variables and say, instead of plotting the individual values of each county, but rather just plot the mean values, then you can see that it starts to linearize. It starts to form a straight line. Same here, unemployed is still in the raw data, but it starts to form a straight line. So it's basically indicating to us that that this relationship can be, if you regress it to the mean, it can be represented as a straight line through that. And indeed, that's exactly what you'll get if you ask SPSS or other tools to add actually a linear line to a scatter plot. It's putting a line through it which represents the average. This line is called the line of least squares. The regression line is drawn in such a way that it minimizes the difference between each of the points and the line itself. That's effectively an average. It's called the line of least squares. And in fact, typical linear regression, standard linear regression is usually referred to as ordinary least squares regression, because it's based on trying to minimize the distance between the points and the line itself, and the differences between the actual values and the points are called the residuals, or the errors, if you like, the residuals. So you'll hear the term residual being used when we get to the regression part and then the demonstration of that. Now, bear in mind that this is, after all, just an average, and we know that averages can be misleading. They often are affected by extreme values, for example. So in the same case, regression analysis here, and it could be that the line is a reasonable representation of a cluster of points, or it could be that the line effectively doesn't represent the data very well. You could have a curvy linear relationship and the line just brutally goes through that. Or you may find that the line itself doesn't represent the majority of the data. It's actually affected by an extreme value. Obviously, just like with an average, the smaller the sample size, the more a single extreme value is likely to have an effect on it. Smaller sample size, the more a single extreme value is likely to have an effect on the linear regression line, the line of least squares. And that's not untypical, of course, of a lot of medical data where you have potentially quite small samples from a clinical trial. And also, you can have situations where you basically just have two values. And here we have a value for everybody has a value of 8 on the x-axis. Looks like a value of 20 or 19 on further on up here. So there's just two values on the x-axis. It still fits a straight line through it. So it's a good idea to visualize the data beforehand, make sure that it can be represented effectively by a straight line by doing things like scatter plots. Now, if we wanted to measure the strength of these linear relationships that we are viewing with scatter plots, we might use something like a correlation value. So whenever we do a scatter plot, we can summarize it in many ways the linear relationship of that using correlation value. If you joined the previous session, you'll know that we introduced correlations. We look at correlations between rating scales. Here we look at correlations between vehicle weight and horsepower. So this is non-medical data, of course. Each of these points represents, in fact, an automobile, a car. And we can see that there's a strong correlation here between vehicle weight and horsepower. Here, that correlation value is represented with a number of 0.859. In fact, if it was a perfect linear relationship, it would just be 1. So it's not quite 1, but it's pretty close. It's getting quite close to 1. If it's a less linear relationship, more of a slightly more random relationship, still, a general trend upwards here. We can see the relationship between time to accelerate from 0 to 60 and miles per gallon. In other words, if the car takes longer to accelerate from 0 to 60, it tends to be more fuel efficient. That's a weaker correlation. Gets you down to 0.4. A negative correlation, this could be, for example, the correlation between blood alcohol and reflex reaction time or something like that. That can be represented as a minus number, but it's, whether it's minus 0.7 or plus 7, it's the same strength. It just indicates that it's a different direction. So correlation values go from +1 to -1, with 0 in the middle. And if it is 0 in the middle, then you're going to get a relationship like this. It just basically indicates that there's no evidence of a linear relationship. There's no strength. There's no, it's effectively a random cloud, or it's certainly something that isn't linear in nature. You should bear in mind, of course, that you can still get, relatively strong correlations here, from a negative correlation here, minus 0.67, even if the relationship is non-linear in nature. So this is a non-linear relationship. You can see I've created this chart by squaring miles per gallon. And in fact, sometimes people linearize relationships when they have these curvy linear relationships by taking things like the log of a value, or by taking the square root of the value, and that can sometimes straighten out the relationship between the two variables and make them more effective predictors in a regression. So a regression coefficient runs from -1 to +1. It turns out if we take those numbers that come out, the correlation coefficient runs from -1 to +1. If we take those numbers out, those correlation values, and we square them, we can turn them into percentages. So if you have a correlation, in this case, of 0.859, and we square that turns into a percentage of 73.8%. And this is known as the R-square value, and it's what's used in linear regression to help us estimate how well the model fits the data. And it basically means that, in this case, 73% of the variation in vehicle weight can be predicted from horsepower, and 73.8% of horsepower, the variation in horsepower, can be predicted from the vehicle weight. In other words, the variations in both variables overlap. Like a Venn diagram is 73% overlapping. And it also means that, obviously, if you have a correlation of 0.4 and you square that, you're going to get a R-square of 0.16, 16%, 5, 25%, correlation of 0.6, 36%. Correlation of 0.7 will get you a R-square value of 0.49. So you're getting almost at the halfway, 0.49%. Okay, so having done that, how can we express linear relationships as predictive models? Well, it turns out that if we have if we're running a regression analysis, and we put a line, let's say it's a simple regression, we just got one variable predicting another variable, like horsepower against vehicle weight here. We put a line through that. Turns out there's an equation that helps you use that line, or helps you to express that line as a predictive model. And the easiest way to think of it is to think about an old adage, like, how long does it take to cook a chicken? And you may get different equations depending on which cook you're looking at. Julia Child says 7 minutes per pound plus 45 minutes. And Julia Smith says it takes 20 minutes per pound plus 20 minutes. Now, it turns out those are regression equations. In fact, the equation for a straight line that we're taught in math at school is y equals mx plus c, and in regression, it's y equals a plus bx. They're exactly the same equation. And there are two elements to the equation. There is the 7 minutes per, that's the coefficient. That's the b value here, or the m value here. And with 20 minutes, there's the plus 45 minutes, or the plus 20 minutes there. That's the area of the C. Basically, it's the constant in the equation. It means that you add on this number at the end. So whenever you run a linear regression, it's going to give you effectively the 20 minutes per, that's the coefficient, and it's going to give you a constant. And if you multiply the values of an independent variable, a predictor variable like blood pressure or something like that, by these coefficients and add on your constant in the end, that is going to give you your estimate. So that is the basis of linear regression. That's what we're going to see when we run a linear regression in SPSS statistics. It's actually going to give us effectively the elements of this equation. We'll be able to apply that potentially if you wanted to copy those numbers out. You could apply them to a new data set and it would produce predictions for you. Okay, so you see here, this is the line going through percent unemployed and percent reliant on public health. So you'll notice that actually when you add the line, SPSS by default literally gives you the y equals mx plus c, or the y equals a plus bx equation here. This is exactly the linear regression equation. Okay, what about if we want to use linear regression to model regional per capita cancer mortality? Let's do that. Let's jump on to a data set here. First of all, I want to explore the data set because I talked about correlations earlier, and this will help me identify where the strongest relationships are within the data. So I'm going to go to analyze up here. In fact, before I even do that, I've got quite a lot of variables here, quite a lot of variables to work with, so it can be a bit confusing. It turns out that if you use utilities define variable sets, it means you can create groups of variables and mask out the ones you don't want to use. And you switch that on by clicking use variable sets. And I'm going to say, don't show me all the variables, just show me the ones I'm using for the regression analysis and any new variables that are created. And I click OK at that point. It just masks out the ones I don't want to use. So now if I want to do a correlation, I'll go to analyze and correlate by variate. And you can see there's a smaller number of fields here. Let's say I want to look at mean per capita cancer mortalities. It's this target death rate here. It just means it's a target field. And we'll look at that against some demographics. So poverty, income, and let's say percentage of health coverage that's public, reliant on provided health coverage. There's only 4 variables there. And if I ask it to do a correlation of that, it'll show me a correlation of each pair of these fields. It's a good idea to switch on, show only the lower triangle, and switch off, show diagonal. It just makes it easier to read the output. We click the output here. Here's the output, so you can see our correlation. So we can see median income per county has a negative correlation with cancer mortalities within that. So it's a minus correlation here. It's not the strongest correlation, but it's certainly statistically significant. It's just basically telling us that as median income increases, cancer mortality tends to go down. Whereas the opposite is true here. Percent in poverty increases, cancer mortality also increases. And if percent of county residents with government-provided health coverage, they're reliant just on government-provided health coverage, they don't have any private health coverage, then that's also positively related to per capita cancer mortalities. But very important here, one of the reasons why we're doing this is to show that these variables here, such as percent in poverty and median income and these other variables here, like health coverage, they're related to each other. So, percent in poverty, population in poverty, is negatively related to median income per county. And that's something to be important for us to be aware of. Because we wanted to use these both as predictors, we have to ask ourselves if they're really measuring the same thing. That's called collinearity. And ideally, in linear regression, you want variables to be reasonably independent of one another. It turns out this correlation is minus 0.789. It's not 0.99. It's not exactly if we're measuring the same thing. There might be a bit of wiggle room here, but it's something we should bear in mind. We should be aware that our variables that we may use to predict things like cancer mortality may themselves be correlated, and that's something at least aware of. Okay, so let's do the first regression analysis. To do our first regression analysis, we're going to go down to analyze here, down to regression, and down to linear. So I'm going to choose linear. You can see there's a lot of different regression techniques here. Linear is the standard one, and I want to look at mean per capita cancer death rate effectively. And I'm going to use things like percentage of public coverage, percentage of healthcare and public coverage, which is one of our predictors. Actually, no, I'll use median income because that's a better illustration of something I want to illustrate. If I click OK at that point, I'll be able to walk you through the basic output of this particular linear regression that we're running, and we'll see the default tables that it produces. So I'll click OK at that point. And the first thing that we see is what's called a model summary here. And it shows this a value here called R, which is 0.429. You may recall that we did correlations earlier on, and the correlation between percent in poverty and mean per capita income was 0.429. Income per county was minus 0.429. Here it ignores the direction. It's basically the same as the correlation. It is the correlation. It's the R value. And as I say, if we square that, that comes out as effectively 184, which is 18.4%. So it means 18% of the variation in per capita cancer mortality can be predicted using median income per county. Now, what we normally quote is what's called the adjusted R. It's usually a little bit smaller, and it's just an adjustment based upon what's called the standard error, which is, a kind of measure of reliability or variance from one sample to the next. So it's a convention that you quote the adjusted R, which is just a little bit, it's usually a tiny bit under the R square if you've got a reasonable sample of data. The next thing we get is actually a statistical test, and this statistical test is called an omnibus test. The omnibus test is just an overall test of saying, does this variable even make a difference? Does it help you in any way predict this outcome? Would it be is it better than just taking the average, or just using a constant? If you just did the constant and said, well, look, I assume that the mean cancer mortality is X. Is using median income more likely to give you a better estimate? And it's usually, if there's any sort of correlation between them, it's usually statistically significant. We would reject the null hypothesis effectively that this variable doesn't help us predict the outcome. And then we get our coefficients table. And our coefficients table here is actually showing us the constant in the equation. So it's saying you're going to add on 225, and for every unit of median income per county, you're going to multiply that by a value of minus 0.001. It's probably a wee bit more detailed than that. If I double click on it, it's minus. You can see it's actually rounding up. It's actually a tiny, tiny number here. So it's saying that a small increase in the median income per county has, in turn, a small decrease effect on the dependent variable, which is cancer mortality. So these two variables are actually statistically significant, and that the standardized coefficient here is basically a standardized version of B. B means beta, it's just labeled beta here. This is the same as our correlation value that we saw earlier on. And it's just telling us that as it's the only field in the model at the moment, that the amount of variation, the amount of the correlation between it and the dependent variable, the unique correlation between it and the dependent variable, is equal to minus 0.4, which we already know. Okay, let's go back, however. Let's have a look at this dependent variable here. So let's have a look at this dependent variable target data. We should really have noticed at the start story, but carried away and got into the regression right away. But let's just have a look at it. So I'm going to switch off display frequency tables. I'm just going to say what's the mean, what's the median, what's the minimum maximum, what's the standard deviation. I'm just using frequencies here, and I'll ask it to do a histogram with a normal distribution curve on the top of it. Click OK on that, and you can see the mean mortality is 178 per 100,000. The median is 178 as well, very close together. The minimum was 59 and the maximum was 362, so a lot of variety there. You can see that this actually looks weirdly normally distributed, quite close to normal distribution. It turns out that in linear regression, data does not have to be normally distributed. It's what's called the standardized resiliency that are expected to be normally distributed. That's the difference between the line and the individual points. So effectively, the regression prediction will it predicts, which is the average, the line least squares, and the points themselves, the residuals we talked about, when they are standardized, that this means when they're the standard numbers, percentiles, in this case have to be Z scores, standardized scores, and that they should, ideally be normally distributed. And if we look at our variable median income here, I just want to click on this and just show me median income, and I'll just give you some summary statistics. You can see that goes from 22,640 up to 125,635. So a lot of difference there in the median income. What happens if I change the units here? Because we did the when we asked for reduced coefficients for us, the regression coefficient, the numbers were really tiny because these numbers are quite large, and these numbers are in 3 digits as well. So something I can do is I can just basically go to transform, and I can ask it to bin the data and put it into something that's a wee bit more intuitive, perhaps. So I can put it into deciles, and I can say, okay, I'm going to pick median income. I'm going to call median inc dec, meaning deciles. Underscore here. That's and this is just a procedure in SPSS that's available in the base. And I can say, okay, look, I want you to use percentiles. I want 9 cut points. That creates a width of 10, so 10%. Twice as 10. Ask it to make the labels to show me where the bottom 10% is. The bottom 10% of those are less than or equal to $34,000. The top 10% of those are over $61,000. It's median income. Click OK. That creates an extra field for me now. I've got a new field at the end here. I right click on that. You can see it comes out, remarkably exactly 10% in each case. You don't always get that, but it's a large enough sample to work with it, and there's a lot of detail in that distribution. If I then rerun the linear regression and I switch this around, so that instead of having individual median income, we've now got the median income decile. Click OK. Run it again. Now it's saying, for every increase in the 10 deciles, so if you're going from the bottom 10% to 20%, that drops the mortality by 4.2%. So suddenly, because we've changed the units, it's actually easier. It's easier to interpret the coefficient, the 20 minutes per, if you like. It has also changed the adjusted R-square. It's actually gone up a little bit, weirdly enough. That might just be because that field smooths out some of the error in the data. What happens if we add in another field? If we go to another field here, we can say, let's look at poverty percent here, and add that in, click OK. Remember, these two fields are related to each other. Well, it's increased a little bit. The adjusted R-square here has gone from previous model summary of 19.7%. It's just gone up a tiny little bit here to 20.8%. And now the coefficient has changed somewhat because in the presence, if you're going to add in the field percent population in poverty, then that field, this coefficient has to change because, of course, they're related to each other. Okay. So now it's saying in the presence of the variable percent population in poverty, every 1 unit increase in median income in deciles drops the percentage of people in the number of people who are dying of cancer by 2.7%, and for every 1 unit, every 1% increase in population in poverty increases it by 0.8%. And now the beta coefficients here. Previously, this was a correlation value. Like, what was it previously? It was let's have a look. Model summary coefficients. Previously, this was minus 0.445. Now it's minus 0.285, and it's actually telling us that this is the amount of unique correlation. If we're controlling for the presence of this other variable, which is not independent of income, of course they're related to each other, then the amount of unique correlation, what's called the partial correlation between this variable and the dependent variable in the presence of percent of population, is dropped now to minus 0.285, and this one is only 0.191. So they're quite weak correlations, but that's not uncommon because they're both kind of measuring to a degree the same thing. Now, in fact, if I go back to this and I change the method, the moment I'm using a method called enter, which is forcing these variables in whether or not they count. I change it to a variable called method called forward. It will create two models and it will stack one model on top of the other, adding each variable. Okay, at that point, you can see here's model one. This is the first variable going in, 0.197. And then model two, we add in the second variable, it jumps to 0.208, only a tiny increase, of course. And in both occasions, the model is, of course, statistically significant. It's better than random. And we get a coefficients table for the first model, which just uses median income. And then the second model, which uses median income and percent. So we can see it being built at this point. Now, at this point, because we've used this method, it actually gives us a thing called collinearity statistic or tolerance. That is a measure that tells you whether or not these two variables are collinear, the degree to which they're collinear. And if that number is below 0.1, it's generally regarded as a problem, the problems in data, because it means that you're basically measuring the same thing, and it means it'll start to mess up the coefficients. It's a good idea that when you're using forward method to explore the data and the independent variables and make sure they're not too strongly correlated with each other. As I add in more fields, I'm going to add in more fields. I've got percent of population in poverty. I've got percent of bachelor's degrees, percent unemployed, percent with public coverage, i.e. percent you're reliant on public healthcare, and percent of married population. So I'm going to add them all in. So now it's going to build a series of models. But in fact, it only built 3. Now, why is that? Well, it's because presumably when it got to the third model, it said I haven't got any more variables here which are going to add much to this model. It's going to bring. So it starts with an adjusted R-squared of 0.233, so 23%. It jumps to 29%. And then just increases it ever so slightly to 29.6%. So 29.6% of the variation. Of course, we don't have any numerical data here, we only have demographic data. So it's very difficult to predict. But nevertheless, nearly a third of the variation in per capita cancer mortality can be predicted from these 3 fields. And the 3 fields that's chosen are percent of county residents aged 25 and over who have attained a bachelor's degree. So basically, graduates. Percent of married households, and percent of county residents aged 16 and over who are employed. These are all negative values, meaning that they drop the proportion. They have a downward effect on the proportion of people dying from cancer on a per capita basis. And if we look at the collinearity statistics in this third one, well, these values are all healthily above 0.1, so they're all bringing something unique to the data, to the model at that stage. So we're trying to say at that point it's not too collinear. It's telling us what the excluded variables were. Excluded variables were median income per county, population and poverty, and percent of county residents. So actually, these collinearity statistics, I should have pointed out, are the ones that haven't been added to it. They are collinear. They haven't been added to this data set, and it's showing you that basically the reasons they haven't been added to because they're not statistically significant because they're only 0.65, but they are sufficiently above the kind of threshold value of 0.1 linear, but they just don't have much statistical energy, if you like, to bring to it to explain variation, so they haven't been added to the model at this stage. Something else that people tend to focus on in linear regression, another assumption, is it assumes, as I said, that the standardized residuals are normally distributed. It also assumes that there's something called homoscedasticity. And if I click on plots here, I can do a analysis here where I look at the standardized, as I said, for standardized predicted values against the, I'm going to put that in the X value, against the standardized residual. Just means the predictions, the values on the line that it uses against the error. And I'm also going to ask for a normality plot. If I click continue that point, okay. When you run this analysis, so you don't, again, it just produces some extra plots for us. This looks, as you can see, very normally distributed. So these these standardized residuals look fairly normally distributed. We have this this line here, this sort of correlation between the observed cumulative probability and the expected cumulative probability. And basically, this is saying if the data points fall on this line of the standardized residuals, it's in many ways it's looking at how well they deviate from this line here, this normal distribution. Let's say if it deviates too much, it's kind of indicating that it's not normal. The standardized residuals are not normally distributed. Here it isn't deviating too much, as we can see, it falls almost straight in the line. That looks fine. But an issue for us is this shape. So we have the regression standardized residuals. This is the error in the model, the difference between the line and the points. And then the predicted values, which is the predictions, the values on the line itself. And if we get this sort of funnel shape, this is called heteroskedasticity. That's a horrible term. It basically means that the variation isn't the same all along the residual values. So it means there's more error at this point. The model's not as sure at this point because there's more error. So it is at this point. And ideally, we want it to be almost skedastic. This means where we get the same sort of variation along it. So there is a little bit of skedasticity here. And it just basically means that when you're looking at these coefficients here, they are going to be sensitive. If we look at these coefficients, they're going to be sensitive to how extreme the values are in the independent variables, and the dependent variables. So these coefficients may be slightly different depending on where you are in the distribution. And one of the ways in which people get around that is that they might, for example, say, well, okay, I'm going to take this sample here, and I'm going to build a regression model for this group, and a regression model for this group, and a regression model for this group. So they split the sample up. That's one way to do it. Otherwise, deal with it to transform data in some ways, and otherwise deal to use more exotic forms of regression. Okay, so that's our walk through linear regression. The last thing we'll be aware of here is just you can't save out the predicted values. That's the unstandardized predicted values. The unstandardized residuals, that's the raw form. You can't export the model as an XML file so that basically exports it as a little package, which you can then apply to new data if it's got the same variance to work. That's us predicting a continuous outcome. What about predicting a category outcome? Well, here for predicting category outcome, we might use something like logistic regression. And logistic regression allows us to predict things that linear regression can't, such as the chance of readmission within 30 days, or the risk of somebody contracting sepsis, or the likelihood of no-shows to an appointment, or the probability of a relapse in treatment or some sort of treatment regime. Even things like likelihood of staff leaving, staff retention likelihood. It produces odds ratios for those people who attended the previous session. We talked about, relative risk ratios and odds ratios. It uses case control studies, and it can model things like the effects of comorbidities on procedure outcomes. So there's a lot of different applications for logistic regression within the healthcare realm. So why do we use logistic regression? Well, because the outcomes are not continuous, and standard linear regression won't work when you've only got a two-category outcome. It just doesn't understand that. So when the outcome consists of two categories, we use what's called binary logistic regression. And when the outcome has three or more categories, we use something called multinomial logistic regression. And logistic regression gets around the limitations of the kind that describes relationships using a straight line, because it's only got, let's say, a two-category outcome here. It uses a special curve. And this special curve is what drives logistic regression. It's called the sigmoid curve. Here, the outcome is not a continuous value in the sense that it's per capita income or per capita mortality. It's actually whether or not you're in group 1 or group 0, whether or not you contracted an illness or did not contract an illness, whether or not you're readmitted within 30 days or not. And what it does is it tries to predict the probability of you being in that group. It fits this curve, and as you attach a variable to that and try to model it here, for example, in a business example, let's say we're selling something like iPhones. we're saying if we give zero discount on it, and in fact, it might even be more expensive than getting off the Apple Store. Probably going to buy it's going to be very, very low. Because we start to add a discount, we get around like 20%, 25%, 28%, 29%. The probability of people actually responding to an offer starts to increase at that point. So this is the principle behind it, that a positive value increases the likelihood of you being in the group, the key outcome group, and the negative value decreases, or lower value decreases that. Yeah. And in fact, there's a special formula that converts the values of the predictor coefficients on the x-axis to these probabilities. And these values that are produced by the regression, by the logistic regression, are not the same as the kind of values that linear regression produces. So it's a little bit more intellectually challenging. The values that logistic regression produces are not things like 20 minutes per pound. For every decile, it has a 2% decrease in mortality or something like that. Instead, it gives you a number that's been transformed. The number that it gives you as a coefficient is actually the log of the odds of being in the higher group, of being in the category low outcome. So that's really difficult for people to get their heads around. So odds are difficult enough, same as probability, but a log of odds is particularly difficult. So it's kind of mysterious in that sense, and there's mathematical reasons for it. But suffice to say that those are the numbers that the logistic regression equation produces. So we can't interpret them directly in the same way that we can in linear regression. The special formula that uses called a link function takes those regression coefficients, puts it through a little formula, and converts everything into a probability. That's what these special numbers are. And you see examples of these special numbers, these log odds being produced, when we try to model logistic regression, or we're trying to use logistic regression to model low birth weight. Let's jump out to a data set there, which shows that. We've got a quick data set there. We have birth weight. And this is our data set. You can see that we've got a category variable here just called low. And if we look at it, there's only 378 cases here. 31% of the cases were women who give birth to low weight children, and 68.8% were normal weight children. You could actually do an analysis because we've actually got the weight of the child as well in there, so we could actually show the two distributions side by side. You could go here to descriptive statistics explorer, for example, and you could put low birth weight, that being the factor variable, birth weight itself in there, and then say, okay, show me some plots for that, and show a histogram. Okay, at that point, it runs out, it tells us what the minimum maximum is for the normal weight in grams, and the minimum maximum is for the low weight in grams. So this is what normal weight looks like, and this is what the low weight looks like in grams. It looks like this one's higher than that one, but in fact, you can see this starts at 2,500, and this one stops at 2,500. There's low weight. These are showing them as box plots here. So this is the cutoff. These are the two distributions. Can we predict which group somebody belongs to using logistic regression? Well, if we go to analyze here, back down to regression again, and to bivariate. Hold on, don't want bivariate correlations. Well, analyze regression. It's binary, not bivariate, binary logistic regression. We're going to put our dependent variable, that's our dependent variable here. Our independents are called covariates. And if I use something like, let me just use something, I just want to point this out. If I use something like a smoking status here, you can see it's coded as 0 and 1. But it turns out this is technically it's a category variable, and what we would normally do is we'd identify it as category. You say this is a category variable. But it actually makes no difference whatsoever when it's coded as 0 or 1. You get exactly the same result, so we don't need to do that. So I'm just going to put that in. You can see I'm using an enter method here. I'm not using forward, did last time. I'm going to click OK at that point. I'm just going to look at default output. So the default output this time starts off and says, look, I'm going to produce a classification table here, which is a little crosstab between what I predict the outcome to be and what the actual outcome is. And it starts with what it calls block 0. It says, I'm going to predict everybody to be normal weight. And the reason it's going to predict everybody to be normal weight is because if it does that, starts with that as a baseline, then it would be 68.8% accurate, so nearly 70% accurate. So of course it says, well, I might as well just assume everyone's going to be on. And then it tells you whether or not this is, this actually helps in some ways. But is it better than random? Well, if you assume that, it is kind of better than random because it's this constant, if you like, it's kind of a constant value saying I'm just going to assume there's 68.8% probability. Does that help? Yeah, it does. It's better than, it doesn't come out as 50-50 or anything like that. It doesn't come out as the original category outcomes, which it's better than 31%. So start to that. And it says it's significant. So the block zero is just saying without anything in the model, how accurate would I be just assuming that everybody's in one of these groups? So that's what it does. And it says, as we put variables into the model, it says, okay, we're going to put some variables in the model. We're going to put smoking status in here. It says, is that statistically significant? It says, yes, it is. So it actually makes a difference. It is significantly related to it. And these statistical tests here are telling us whether or not that's better than our standard model, which just uses a constant. It actually tries to give us some R-square values. So the R-square values are really, really small numbers. I wouldn't pay too much attention to them, but the larger, to think of them as R-squares, the larger they are, the better the model. More typically, people use this number here, which is called -2 log likelihood. It doesn't mean anything in reality, but if you wanted to compare one model to the next, the smaller the number is, the better the fit of the model. So a model with a number of 459 compared to a model with a number 259. 259 would be a better fit because this is a measure of error, if you like. And then this is the classification table. The classification table hasn't changed here. But I wouldn't worry too much about that. It will only change if it starts to find cases where there is more than a 50% chance that it's in the low birth weight group. And it might not find cases where there's a more than 50% chance being in a low birth weight group. It might find some that have 45% chance, 0.45. So that's not over 50%. So it will still classify them as being normal weight. But the probability values that the model will produce for us are really useful because, of course, we'll be able to find people who have an elevated risk of having low birth weight. And here it tells us that smoking during pregnancy, we've got a constant here. Constant is just this minus number, that's the log of the odds. This value here is 0.704. It's a small value. It's actually the log of the odds. We can't really interpret it directly, but it's a positive number. And it's telling us that because code 1 equals that means that people smoked, and code 0 means that they didn't. And because code 1 here indicates that people had a low birth weight baby, and code 0 means that a normal birth weight baby, it means that you're getting a positive number, which means that it increases the risk of having a low birth weight. And in fact, this is statistically significant. And the one number that does give us, which is really useful for us, is log odds. It gives us these log odds. It gives us these odds ratio variables that values that we saw earlier on. The odds ratio value here is called an exponentiated b value. So the exponentiated b, the xb value here, is the ratio of the odds of an event occurring for 1 unit change in the predictor. For example, if the exponentiated value is 2, then the odds of delivering a birth weight baby for someone who smokes, for example, is 2 times the odds of a low birth weight baby for someone who doesn't smoke. And that's why it's so useful. The hard part is that that's not the same as saying it's twice as likely to happen, because these are not probabilities, these are odds. But here it's pretty much total. So it's saying the odds are 2 times higher if you smoke during pregnancy to have a low birth weight baby. If we add in another variable here, I'm going to add in race. Now, race this time isn't coded as 1 and 0. It's actually got 3. It's got 3 categories here: white, black, other. So this is old data, so it should say ethnicity or something more appropriate. But it says race here. So this time I do have to identify this as a category field. So it's the categorical field. And the categorical field says, okay, I'm going to choose one of these categories. And I'm going to use that as what's called a reference category. So when we see the coefficients for the other categories, it's telling us the effect of not being that reference category. So the reference category here will be the first value. I think it's the first value, which is white. And then we've got black other. So let's click OK at that point. We're using enter again, so we're forcing them in. And now the R-square, is the R-square value slightly higher or is it lower? Let's see, the -2 log likelihood. Let's have a look. Model summary here compared to previous model summary. 459,036. So model summary here. 439, so slightly lower, and 105. So it does look like the fit's increase. You can see that starting now to pick up some low birth weight babies. So it's finding some which have a more than 50% chance of being low birth weight. And here it's saying here at smoking during pregnancy, this time the exponentiated B is actually in the presence of these other values is actually 3 times. The odds have gone up. So 3 times. All of these values are statistically significant. And it's saying the effect of being race 1 refers to black people, the effect of being black versus white actually increases by the odds of you having a baby by 2.9 times. And the effect of being in the other non-ethnic, other group, meaning Asian and all other ethnicities and not being white, increases it by 3. These are all statistically significant at this point, and the constant's getting smaller as it becomes less important. That's how we can add in a category field by paying attention to what is the reference category. In this case, the reference category is whether or not people are white. And then we can add in other factors here, like whether or not they have a history of hypertension, whether or not there's a presence of uterine irritability. We can add those in. And the values are starting going up. The -2 log likelihood values going down. So the fit increasing. It's a little bit better this time. So percentage accurate is 69%. It's still liable to predict using this model, still liable to predict some people as having a low birth weight baby when in fact they don't. Normal weight baby. But these are all statistically significant. So if we use the forward method, they would all go in that model we would expect. And we can add in other fields like number of physician visits and weight of mother at last menstrual cycle, and history of premature labor. So now we're adding all of these fields and click OK. Let's see what happens now. So we chuck everything in. R-square has now gone to 0.2. You can see that the percentage correct case is being classified as 74% correct. It's doing a better job at identifying low birth weight babies. But number of physician visits in the presence of all of these other factors is not statistically significant. So we probably shouldn't use that one. That's not statistically significant. So number of physician visits during the first trimester, not statistically significant. We probably wouldn't use that. So we could at this stage, we could see which ones are getting added in one at a time. I would probably use forward LR, forward likelihood ratio, click OK at that point. It's obviously going to build a model for us, and it's going to show us the variables not in the equation at step 1. It was step 1, step 2, step 3, step 4, step 6. So put in 6 variables. You can see the -2 log likelihood values as the variable, as the number increases, as the number of fields being added in increases. That gets smaller as a better fit. And the Michael-Kirky value gets higher as each variable is added to it. Here's our classification table for each model as we're adding in 6 variables. We've got variables in the equation here until we get down to step 6 here. And we can see we end up with race, history of hypertension, presence of uterine irritability, weight at last menstrual period in pounds, and history of premature labor. These are what end up, and smoking status during pregnancy. These are what end up being added to the model or final model using forward LR. And it actually tells you whether or not if you remove each of these terms, each of these factors, whether or not it would make a statistically significant difference to it. And you want these all to be statistically significant, less than 0.05. It gives us information on variables not in the equation. Now, if we asked it to save the results from this, instead of just saving the category that you're in, group membership, probably what you're really interested in is the probability. And again, I could save this away. I could say, okay, let's export this as a little package file so I can apply it to a new data set. Click OK at that point, it reruns it, and we come back to the data here. You can see it says, I'm predicting this person to be normal weight. Why? Because the probability of them being in the high birth rate group is 0.28, that's 28%, maybe 29% here. 17%, I'm going to predict them to be 30% chance of them being in the low birth weight group. 45%. You can see they're starting to get to some groups here where it's 45% chance of them being low birth weight. It's quite high, but so far it looks all right. So as we get down to the predictions for the low weight, you can see that these are over 50%. So this variable here is showing us a mean of 31% chance, minimum 4% chance, maximum 82% chance. That's the variable that we would use to test the risk effectively for each individual case, and that's what logistic regression is creating for us when we run that procedure. Okay, that's using logistic regression. Bear in mind that FSS statistics has a lot of regression methods. The regression models module adds several key methods, including logistic regression. You'll see multinomial logistic. That's when you have more than two category outcomes on medium high. And there are many additional methods that are made available through SPSS integration of R and Python. So you'll see some of these little ones popping up here, plus symbols that may indicate that it's using R or Python to run that procedure. Some additional resources that you might want to be aware of. We have information on how to model nonlinear relationships, as well as introduction to things like moderation analysis and mediation analysis. If you're aware of that, it's based on linear regression. Another useful resources that show videos, such as see what's included in the regression model, previous recorded webinars, test or interpreting significance tests, and a blog series on the basics of statistical inference. You should be aware that we provide a portfolio of online training materials free to existing SmartFishing customers or available for purchase, non-customers. And we have a number of consultancy packages that we provide to people, whether it's one to 2 days worth of work or whether it's a more involved engagement. You can source your SPSS software directly from us, often with discounts. And you should be aware, as we say, we have training consultancy services. We generally offer no strings attached technical and business advice to anybody who comes to us. And we offer formal technical support services around SPSS statistics. If you're a customer of ours and you've got a copy of SPSS, we offer formal technical support around that directly from our own experts. I hope you find that useful, and we look forward to you logging in again in the future. You might want to check out our website to see what webinars we have coming up in the near future. Thanks very much.